Good, let's take off here again. So we had in the discussion just before the break the definition of entropy production, and I wrote it here, I think, in a more complete form than before the break. And we arrived at this expression here for the entropy production. And then I said you can rewrite this in different forms. And the most important one, or both are important actually, but the most straightforward one is this one first, where you can add the pj/pi's in the logarithm, and it's still valid. And then we said this is a very useful form for this quantity because it lends a very natural interpretation saying that as soon as you deviate from detailed balance, the argument of the logarithm is distinct from 1. So you can have entropy production, and that's a measure then of the irreversibility of your process. Why is it that you do have the equivalence of this here? So this is basically because of global balance. Global balance means that if I sum over all j, and I have here bj omega from j to I, then this global condition means that I also have this in the reverse direction. So I can add this here. I have here minus pi omega I going to j. This has to be equal to 0. This is not detailed balance because I'm summing over all states. It's the global balance condition. And when you use this global balance condition, and you can show that the sum over I and j, pj wij of the logarithm of pi to pj is actually 0 by using global balance and interchanging indices because they are dummy indices in this double sum over I and j. Okay? And this here follows in a very similar fashion by a very basic algebra. It's a natural thing to decompose the entropy production into because you have here a current. That's the net current between the states I and j. It's 0 if there's detailed balance. It's non-vanishing if there is broken detailed balance. So it's these currents that you see here as the prefactor. And the argument of the logarithm is the forward and backward currents between the states I and j. Let me list a few properties of this entropy production. You can show, I'm not going to show this to you, it's quite straightforward, that sigma is always positive, and that's by using Jensen's inequality to show that. You can also show that sigma is 0 if and only if there is detailed balance. And that means then that sigma greater than 0 is a measure of irreversibility of a steady state and of a steady state that's called a non-equilibrium steady state, and that's often abbreviated as NESS. All right. That's how far I would like to go with characterization of Markov processes. And now let's come to an example. Okay, so what I want to do now is to go with you through a rather elementary example, but it was very important in the history of statistical physics. It's a model that was developed by the Ehrenfests, and the Ehrenfests wanted to illustrate with that why a reversible system can be irreversible in the sense that it goes to a steady state. Okay, so from an arbitrary initial state where you would think of, say, two boxes of particles where you have initially all particles on the left-hand side or the right-hand side, and then over time you observe that they become equally distributed between the left and the right. Or you have spins which are up and down, and you start from something that has only spins up or spin down, and you are at high temperatures, and then you observe over time there's an equal distribution of spins up and down. So how is that? Given the fact that the underlying process is actually reversible. How does a system approach a steady state in a manner that seems to show some relaxation behavior? Let us explore that a bit. The Ehrenfest model also has a caricature. It's called the dog-flea model. So instead of two boxes with particles, you can think of two dogs. Let's call them Alice and Bob. And you have particles, fleas on Alice and fleas on Bob. And they hop back and forth between the two. And you want to know how is a steady state established between the fleas that you have on Alice and Bob. So let's define this flea model and then go through the arguments. So it is a stochastic process. You have a random variable, which is the number of fleas that you can have, say, on Alice. And the number of fleas can be anything between 0 and an upper number of these fleas, and let's call this n. If I want to describe this in terms of a stochastic process, I need to give you the corresponding transition rates between the states n and n minus 1. So let's say that you are on Alice, and Alice has a rate of lambda of losing fleas to Bob. Then this is the per capita loss rate times n. Okay, this is the loss of fleas from A to B. You can also have a gain, n going to n plus 1. That means the fleas have to come from Bob, and let's say that the rate is the same. So with the same rate that you lose fleas to Bob, you gain from Bob, but then the corresponding rate has to be the size of the population on Bob, and that's the complement of n, so n minus n. That's the rates that we have. Of course, you can write down the master equation, but I don't do. It's kind of obvious how you would actually write it down. Let's just go right into analyzing the steady state. Why is that easy? It's again easy because it's a one-dimensional line that defines the topology of your process. So it's a one-step process, and therefore it obeys detailed balance, since you can cut through this one-dimensional line at any point, and there must be detailed balance. So this must obey detailed balance. There's also no absorbing state, right? Because any flea can hop back and forth as it likes. And that means now I do have this detailed balance condition. So let's write it out. The probability to have n fleas on one of the dogs times the probability of transitioning to the other dog is the probability of doing the reverse. I'm having n minus 1 fleas, and I have a hop backward from the other dog, and the probability for that is lambda minus n minus 1. This is a recursion relation. And once you have a recursion relation, it's quite straightforward to calculate the whole distribution function. You just start from P0 and you work your way up to P1 to P2, etc. Then you're left with a normalization constant, P0, but you can fix that by normalization. Probability has to be such that the sum over Pn is 1. So you use sum over n, Pn equal to 1, and you work out the result of the recursion relation, and what you find is that from detailed balance, the steady state distribution must be a binomial distribution. So it's the probability of picking n, small n from large n, the full population, divided by 2 to the n. Okay. And note, I did not use any statistical mechanics argument here of equal probability or something like that to get the steady state. It's a dynamic argument based on detailed balance that gives you that result. So we know that this process, whatever you start from, will even out the population such that you have a binomial distribution between the two. That means the average of, so that implies that the average is n over 2, and the deviation is 1 over 2 square root of n. That means the larger the population is, the smaller the variance, and the closer I will be to an even distribution of fleas between Alice and Bob. So far, so good. But how does the system get there, and how do we understand the approach to equilibrium from a system that has reversibility? Reversibility in our case is a reversibility in terms of probabilities, because we don't have a deterministic process. We define everything in terms of stochastic dynamics. And as you heard now from me several times, is that reversibility means that the forward path in probability equals the corresponding backward path. Okay? So if I, for example, say that at some time t, all my fleas are on Alice, and at time t plus tau, the probability is that Alice has n over 2 fleas. Okay? So that probability of these two events at time t and time t plus tau is equal to the probability of the reverse. That means that I start with an even number of fleas between Alice and Bob, and I arrive at time T plus tau with a situation that there's none of the fleas on Bob. All of them are on Alice. Okay? And that sounds a bit weird. Okay? Right? Intuitively, you would say, oh, there can't be. There must be an asymmetry here. The point is there is no asymmetry in this quantity because that's the full joint probability density for the forward path, and this is the full joint probability of the backward path. The way you think, I guess, is you think in terms of conditional probabilities. You think given that I have so and so many fleas on one of the dogs, what's the probability of having another number at some time later? Okay? And conditional probabilities, they are, of course, very, very asymmetric. But joint probabilities are not. They are, because the system is reversible, they are completely symmetric in exchanging the events. Okay? So let's formalize that a bit. So we do have 1 equals the joint probability n over 2 t plus tau n comma t, and the reverse, so p n t plus tau n over 2 at t. That's the same. Okay, that's reversibility. And now let's write this in terms of conditional probabilities. So that means, by definition, this is n over 2 at t plus tau, given that I had n at time t, but times now the probability of that state. And I do the same here for the denominator. This is p of n t plus tau, given that I have n over 2 at t, times the probability of n over 2. Okay, now just use that relation that we have there and write now the ratio of conditional probabilities. So the likelihood of transitioning from all fleas to half of them divided by the reverse happening, so transitioning from half to all. This is then given by Pn over 2 by Pn. You can write this out. This is then, as you insert what we have there, that's n factorial over n minus n half factorial, n half factorial, just using the binomial distribution and the binomial coefficients. Well, but if you use Stirling's formula, this is 2 to the n. Okay, and that's a astronomical number. This is much, much, much larger than 1. And that means that going from a state where you have all fleas accumulated in one dog to a distribution closer to the equilibrium is far more likely than going the other way around. So an essential part, and like Piles is the first to express this in a very clear way, of irreversibility is connected with the fact how you ask the question. So it's always connected with the initial state that you fix, and then you ask, given that initial state, what's the most likely cause of events that's going to happen? And the answer here is, given the initial state of having a very uneven distribution of fleas between the two dogs, the most likely cause of events is that it's going to go towards an even distribution of fleas between the two dogs. Okay. So it's really key that we distinguish joint probabilities and conditional probabilities, since they ask very different questions. All right, now let me show you. Okay, these are questions that we ask. What is the equilibrium state? How is it approached? And what's the nature of the state? Now let's look at some simulations. In these simulations, first look on the left-hand side. What you see is the early time evolution. You start from a situation not really shown, that you have none of the fleas are on Alice. So that's your initial condition. And then you let the dynamics evolve, and you see for different realizations of the stochastic process, there's always a trend to go towards an even distribution. That's clear, because if you start from a configuration where all fleas are on Bob, the only possible event at first is that a flea hops to Alice. And then as you continue doing so, you have 49 of 50 on one of the dogs, so it's more likely that you will have jumping from Bob to Alice, until you do have an even distribution between the two, and then it's kind of even of picking the fleas on the two dogs. And then system starts to quote equilibrate, and that you see by the fact that at long times the probability the trajectories, they fluctuate back and forth around the mean value between having a little more, a little less of fleas on one or the other dog. And what I gave you here in addition is the green line shows the sigma deviation, so a half square root of n. And within that sigma deviation, you roughly have something like 95% of all the events that happen in the system. Good, now let's link this maybe a bit to your picture from statistical physics. Okay. So how would you argue there? You would say there is a certain number of microstates, meaning which of the fleas is on which dog in detail, and there's a certain number of macrostates. So let's specify that. You have a microstate, and there I would say this is all the sigma i's, which means now is flea 1, 2, up to n on Alice or Bob. So sigma I is an element of plus and minus 1. And plus and minus 1 simply means that the flea is on A or on B. Okay, a macrostate would just be that you specify the number n, which is the number of fleas that you have on A. You don't really care about which flea is where, you just want to know how many of fleas are on one of the dogs. Okay, how many microstates does this macrostate have? There's two choices, right? In total, the total number of microstates, like a spin chain, right? This is 2 to the n. Each one can be on A or B, up or down, left or right box. And then you say, let's assume that they're all equally likely. That's an assumption now. And from that equally likelihood of the microstate, let's calculate the probability of having n of the fleas on one of the dogs. Well, it's a counting problem. you have to say how many possibilities do you have. This is 2 to the n. And how many of those are to your favor? This is the binomial coefficient. Okay? So you get the same kind of distribution from a counting argument based on equal likelihood in statistical physics. Right? Now let me show you the final distribution. So when you are in this final steady state, you have a binomial distribution, which is the asymptotic solution that you must get for long times. And this here compares simulations with a corresponding analytic solution and agrees, of course, quite nicely, quite well. Now let's ask a final question. But before let's do this. Before let's take the message home. So what are the basic insights that we gain from this simple analysis of the dog-flea model? We have seen that the starting point that we took, which is distinct from the starting point you usually have in statistical physics, gives you an answer that it's overwhelmingly likely that the system will go to a state with an even distribution of fleas between the dogs. In equilibrium, so after this initial transient, if you go back in the trajectories, there was this initial transient here roughly between time 0 and something like 30 or 50. The initial state mattered, and there was a sense of time, because the initial condition fixed something very unlikely. And then you have a sense of time until you reach a state where you forget about the initial condition. Now I'm using metaphors. And then from that time point on, you can look forward and backward in time and you will see no difference. So in equilibrium, after the initial transient, after this transient behavior has died out, you have no sense of time. If you want to know how likely are these crazy events that Alice or Bob lose their fleas, which would be nice for both of them, this is super unlikely. Right? This happens because there's a conditional probability with a likelihood of 2 to the minus n, which is just not happening. Okay? And the statistical definition of time here is one where you always talk about conditional probabilities. So you fix an initial condition and you want to know where do you go from there. Do you go into a more or less likely situation? And the direction of time is such that in these processes you go from a less likely to a more likely state. All right, now let's go and talk about entropy. So let's talk about entropy as you know it. In a course in statistical physics or advanced statistical physics, depending on who teaches it, you define a statistical entropy, which is the sum over all microstates, and then you have P log P in the argument. So you have P of the microstates at time t, and the log of P of these microstates at time t. That's the statistical entropy or Shannon entropy that you can define for the probability of the microstate, right? That's what I'm specifying here. You can relate this to a probability that we defined. The object that we looked at was the probability of a macrostate. And since the fleas are all identical, it's very easy to calculate from the probability of the microstate the probability of the macrostate, because the prefactor is just the factor of degeneracy of the microstate. So that's the binomial factor n out of n, and the sigma i's are such that they have the condition that you have n fleas on dog A. Okay, so when you look at that, you can then write the entropy in a different form. It has the entropy in the same functional form as the statistical entropy, but now for the macroscopic object, the macroscopic probability distribution function. And then there's an entropy term that's missing, and that's basically coming from this factor of redundancy or degeneracy, and that's counting that you can distribute in n over n ways the fleas between the two dogs, and that doesn't change the number, doesn't change the configuration. So it's basically a Boltzmann-like term where you say Boltzmann entropy is the log of the number of states, and here it's weighted by the likelihood of being in that macro state. Okay? You don't have to use my arguments in words to show this. You can really formally start from the macroscopic expression, use this definition here or this relation, and work this out. Okay? But that also has a very neat and immediate interpretation. All right, so that's the entropy for that. And now let's see how this entropy evolves in time. So this entropy that I just took from statistical physics and rewrote it in terms of the probability Pn of t. This probability S of t here shows the standard behavior that you would expect from statistical physics. You have it's starting from 0 because you pick a very unlikely state, say just one set of fleas on one dog and none on the other. Then you see the entropy becomes larger and larger, and it saturates. It saturates where? Yeah, at the point where you have a completely equally likelihood of fleas being between the dogs. So that's log 50, basically. All right, now there's another quantity that I showed here. This goes down in time. And let me write this on the board as well. So the other quantity is a different measure that you can define. It's called h of t, and that has the name of Kullback-Leibler divergence. And I explain it after I've written it down. So you sum also over n, you have Pn of t, and you have the log of Pn of t divided by Pn. It's an object that contains the actual probability density, Pn, but it also contains the equilibrium probability density, Pn. So it measures how far the time evolution of the probability density is from or diverges from the final steady state. Once this probability is equal to Pn, the log is 1, so this Kullback-Leibler divergence is 0. You don't deviate anymore from the final steady state. So it gives you a measure of how the deviation of Pn of t from Pn goes to 0 in our case here. So it's a deviation measure from equilibrium, and it's as useful as the entropy. Actually, it's the same as the entropy, because you can show, and that's again a very elementary calculation. It's the asymptotic value of the entropy minus S of t. So as S infinity is just S at t equal to infinity, and S of t is the quantity that we just calculated, and S infinity, right, this is just the log of 2 to the n. Okay. Let me show this to you again. Okay, so here you see the entropy and here the Kullback-Leibler divergence. It starts from some large value, but then ultimately approaches a steady state such that the deviation from the entropy in the final state is actually 0. Is there entropy production? Not really in the final state, because the final state is a detailed balance state. There can be no entropy production. But along the way, there can be, because the statement about entropy production that we made is one about the final steady state. And here we had initial transients who actually have entropy reduced along the way. That's kind of obvious too. If you start from a situation where you have a nice and shiny dog, and the other one is dirty with all the fleas, okay? There's entropy produced initially because your nice and shiny dog gets dirty with fleas. But after that, after there's a steady state and both dogs have the same amount of fleas, the entropy production goes to 0.